Welcome to a quick video on function notation and its interpretation. The question for you to be thinking about is how function notation is used to express facts and questions about functions and the situations they describe. Here on the screen we have somebody doing the luge. This was discussed in the instruction on this page as well as in your discussion. So you can see that the individual sits on their back or lies on their back and then goes down a steep decline made of ice. The goal is to be the fastest. Let's start this lesson. When we start, also keep in mind these basic questions. What types of relationships between variables are called functions? And how is function notation used to express facts and questions about functions and the situations they describe? Let's look at these luge runtimes. In this table here and graph, we can see that vertical drop and runtime in seconds are related to form this shape. Now, if we look at this shape, would we say this is a linear relationship or a nonlinear relationship? Based on the fact that this is not a straight line, we would say it's a nonlinear relationship. Now let's answer the questions. How is the fact that f of 50 equals 64 shown on the graph? Well, what does this mean? We first need to understand function notation. This means that f of 50 equals 64. In other words, when x is 50, y is going to be 64. Looking here on the graph, I can go to where x is 50. If I move up, I can see then my y value is truly approximately 64. It looks like these tick marks or these intervals go by 25 seconds. So if this is 75, then this is approximately 64. And that's how this is shown on the graph. Now pause the video and see if you can answer letters B through E on your own, and then come back when you think you're ready. All right, let's go through B here. What value of y satisfies the equation y equals f of 40? Well, we can see right here that we're looking for a y value when our x value is in fact 40. If I go to 40 and I go up, I can see that my y value is pretty close to 75, or maybe 74, so it's approximately 74 seconds. How about C? What value of x satisfies the equation 51 equals f of x? Well, now notice I'm looking for x, no longer y. I have my y value, and that's 51. So if I go right here to approximately 51 and then scroll along this grid, I can see that it intersects here, and my y value is right here at approximately 78 meters. Notice that I'm describing this as meters because this is my x-axis or my independent variable. Let's go to D now. For D, what values of y, so now I'm looking for y, satisfies the equation y equals f of 10. Well, my x value is 10. What is my y value? Here's 10. My y value is up here at about 150 seconds. And the last one, what values of x, so now I'm looking for x, satisfies the equation 45 equals f of x. Well, 45 is my y value, and it's maybe about here. So my x value for that is around 100. And again, make sure that you describe what this value represents, and that's meters. You should remember that this x-axis here is your independent variable, and the y-axis is your dependent variable. It depends on your x-axis. So the runtime for the luge depends on the vertical drop. And you can see in this table, the greater the vertical drop, the faster the runtime. So in other words, the steeper, faster somebody goes down. Let's move on. In this next case here, we're talking about bouncing balls. We know that gravity has the same effect on all objects, whether it's somebody on a luge course or a ball dropping from a tower. The only thing is that because a ball bounces, gravity has to continue to act on it over and over and over again until it stops bouncing. Another thing we should notice is that when we are dealing with a contextual situation, it's good to use letters for our notation. So this is part of our function notation. Our independent axis here is time, so we could call that t. Our dependent axis, our y-axis, is height. So we could call that h of t, meaning height as a function of time. Let's use this graph to estimate answers for these questions. Go ahead and pause the video once more, see if you can answer these questions, and then come back and let's do them together. For the first one, what information is expressed by h of 0 equals 10? Well, in order to answer that question, we need to know where this is. Well, when x is 0, h is 10. In other words, when our time is 0, our height is right up here at 10. What does that mean? Try to visualize the situation. Before we have even started timing, the ball is sitting up here at a height of 10 feet. We haven't dropped it yet. So this is our starting height, and we can write that in. This is our start height when time is 0. How about this one? What is the value of h of 4? Well, think about where this 4 is. 4 represents time. This is our x-axis. This is our x value. So at 4, right here, when I look up here on our graph, I can see that our height is about 7 seconds. Or 7 feet, sorry. Then on C, what values of t satisfy the equation h of t equals 8? Well, h right there, that represents our height, or our y value. So up here there's a pink dashed line drawn where our height is 8 feet. Notice that we have more than one answer. We have an answer here at about 0.25 of a second, and another answer here at about 1.5. So let's mark those down. Maybe 0.25 and 1.5 seconds. So we can actually have more than one answer given a y value. We can have more than one x value given a single y value. But we'll be examining if we can do it in the reverse on the next slide. What is the value of h of 1? Well, again, 1 represents our x value. So if I go to 1 and I mark right here on our graph, I can see that the y value is clearly 4 feet. And the final question, what values of t satisfy the equation h of t equals 0? So when y is 0, where is y 0? Y is 0 all the way down here along our x-axis. And what I want to know is what values of t satisfy that equation. So in other words, what x values? Here's an x value, here's an x value, and here's an x value. Again, I have multiple x values, and here's an x value. That will give me this single y value. Now recall that in a relationship between two variables x and y is a function of x when there is exactly one y value corresponding to each given x value. So in other words, if I have an x value of 2, it can only have one y value of 1. So for example, if I had a value of 2 and had another y value of 3, then this would not be a function. But in our other example, I had a y value of 1, but I had multiple x values. So maybe 2, maybe 3. In this situation, this is okay. This still represents a function, whereas this does not. Now pause the video and see then if you can explain why the height of a bouncing ball is in fact a function of time, since it was dropped. To explain this, you can use the logic we just used. Each x value here is mapped to only one y value, so in fact it's a function. Now let's explain why light intensity is a function of distance from light source to receiving surface. In this case, the intensity of the light on the plant depends upon the height of the plant. So the height of the plant is the independent or x variable. As this grows, our intensity grows. But notice we only have one y value that corresponds to each of the x values. So depending on the height of this plant, there is only one intensity. And finally, C, explain why length of the shadow cast by a tall building is a function of the time of day and time of the year. Again, for these problems, it helps to determine which is the independent and which is the dependent variable. So for this problem, our independent variable x would obviously be time of day and time of year. Our dependent variable y is going to end up being the length of the shadow. So the length of the shadow depends upon the time of the year. And as we know, the length of the shadow changes for each x value. So in this case, there is only one y value or one length given the time of the day or the time of the year. Let's wrap this up by looking at some non-functions. Because at this point, it may seem that all relations between variables are functions, but truly that's not the case. We can recognize non-functions by studying patterns in tables and graphs, values, and rules relating variables. In this first example, there's a relationship between height and age for a group of 20 people. Here's what it looks like on a scatter plot. Can you explain why this is a non-function? Hopefully you can explain by saying that if we look at our x values, so say we're looking at an x value here on the graph of maybe approximately 4. For this x value, it looks to me like we have multiple, maybe even 4 y values. And we know that we can't do that. So this cannot be a function. We also have similar issues here and here, as well as right here at 15, age 15. So this does not meet our rules for a function. How about this? The relation between fuel efficiency, y, and weight, x, of a car. Is that a function? Well, we could probably say that there is a relationship between the fuel efficiency and the weight. Fuel efficiency probably does depend on the weight. However, we can't say for certain that given a certain weight, we don't have cars that have the same fuel efficiency. So it's not a function. Let's look at C. This one's easy. Why isn't this a function? Notice in this case we have the same x value mapped to 2 different y values. Therefore, that's not a function. Finally, in D, notice that if we pick an x value anywhere here, we get a y value and another y value. This would be shown to not pass something called the vertical line test. If I pick an x value and there's 2 y values, it's not a function. And this is just a window that was used in the calculator. Now that we've come to a conclusion, I want you to think and be able to explain why time is not a function of height in the bouncing ball experiment. So think about that. Why isn't time a function of height?